Welcome everyone. During this lecture we're going to introduce the definition of power, and we'll also explore an application involving power. Let's define power. Power is a measure of the rate at which work is being produced with respect to time. And so power has two components. First of all, work must be produced, and second of all, we must consider the amount of time that it takes to produce this work. For example, someone or something that can produce a lot of work in a short amount of time is said to be powerful. Let's introduce the equation for average power. Average power, which is abbreviated as P with a bar on top, is simply defined as the work divided by time. It also equals energy divided by time. The units for average power are, well, let's take a look. Work has units of joules, and time is measured in seconds. And as it turns out, a joule per second is called a watt. So power is measured in units called watts. We will now derive another equation that describes average power. As you probably recall, work is defined as force times displacement times the cosine of the angle between the force and the displacement. And let's assume that the force that we're applying is parallel to the displacement. Under those circumstances, the angle is 0 degrees and the cosine of 0 is just 1. So we'll define work as just force times the displacement, again with the understanding that the applied force is parallel to the displacement. Let's now substitute this expression into the work equation. If we do so, then the average power becomes force times displacement divided by time. And we can indicate the time as delta t, and I'll show you why. I'd like to indicate it as delta t because we have introduced delta x over delta t earlier in the semester. Do you recall the definition of delta x over delta t? It turns out that delta x over delta t was defined earlier as average velocity. Therefore, average power can also be expressed as the force times the average velocity that an object is experiencing. Of course, let's keep in mind that the force is the parallel component of force. And so we'll indicate that with two parallel lines. Again, this equation works when the force applied is directed in a parallel fashion with respect to the displacement as well as the velocity. And so we have developed two equations for average power. The first one is work divided by time. And the second power equation, of course, is force times average velocity. And we will place these two equations in a box. Now, let's take a look at the units for a second time. Power is expressed in units called watts, and we're familiar with this unit. We've heard watts with respect to the rating of a light bulb. Toaster ovens are rated in terms of wattage, so are blow dryers and so forth. And so how is the watt associated with these objects? Because these objects don't do any work, right? Power equals work divided by time. Well, it turns out that these objects do produce energy. A light bulb produces light energy as well as heat energy. So does a toaster oven. The filament within a toaster oven produces a little bit of light and a lot of heat. And same goes for a blow dryer. So the power rating measures the amount of energy that's being produced by these objects with respect to time. Another thing to consider is the fact that we as human beings produce heat energy as well. How does the heat produced by a person compare to the heat produced by a blow dryer or by a light bulb? Do you think that a person produces the same amount of heat as, say, a 25-watt light bulb, a 50-watt light bulb, a 100-watt light bulb? It turns out that the average person generates approximately 70 watts of power. That means that the average person generates 70 joules of energy every second. And this goes on indefinitely. 70 joules of energy are being produced by a person every second on average. We will now introduce the definition of instantaneous power. Instantaneous power is a measure of the power that is being produced at a specific instant in time. The symbol for instantaneous power is just P without a bar on top of it. And the equation for it is force times velocity. And this means final velocity as opposed to average velocity. And of course, it has the same units as average power. Let's now introduce the definition of a horsepower. Horsepower is a measure of the average power that can be produced by an average horse over an extended period of time. Horsepower was a very practical unit a long time ago when machines were primarily powered by farm animals such as horses and oxen and so forth. It's amazing that we still use horsepower to describe the power of modern technology. If you're wondering how many watts the average horse can produce over an extended period of time, I have the answer for you. 1 horsepower, which we'll abbreviate as HP, equals 746 watts. I have a question. Can a person produce a horsepower? Well, the answer is yes, a person can produce a horsepower, even though a person is not as powerful as a horse. What will happen is if a person's producing a horsepower, that person will get tired very, very quickly. Whereas a horse can produce a horsepower continuously over a long period of time without getting tired. Also, a horse can produce 10 horsepower. However, if we force a horse to produce 10 horsepower, that horse would get tired after a short amount of time. We will now introduce an application of power. In this example, a car of mass m equals 1,200 kilograms starts from rest and travels toward the top of a 75-meter incline as a result of the power delivered by its engine. If the car's acceleration equals 5 meters per second squared, draw a free body diagram and determine the magnitude of the frictional force. The first thing to note is that we have a car on an incline, and therefore we have to do some prep work in order to determine Wx and Wy. Of course, the weight is just given by mass times gravitational acceleration. The mass of this car is 1,200 kilograms times 9.8, and that yields 11,760 newtons for the weight. Wx is given by W times the sine of the angle, and notice that we have a 30-degree angle within the incline, and so if we multiply 11,760 by the sine of 30, the result is 5880 for Wx. Finally, for Wy, we can use the equation W times the cosine of theta, which of course equals 11,760 times the cosine of 30, and that outcome is 10,184 newtons. Next, we'll construct a free body diagram on the car. There's our car lying along the x-axis of a Cartesian coordinate system, and we will now introduce the forces that are acting upon it. Of course, we have Wx acting on the car, and Wx is always directed toward the bottom of an incline. So here is the way that we would represent W sub x. W sub y always lies down along the y-axis. So here's W sub y. We have the normal force acting up along the y-axis. And it's important to note that if the engine is driving the car towards the top of the incline, it produces a frictional force, or I should say it compels the production of a frictional force between the road and the drive tires, and that force actually acts in the direction of the car's motion. So the frictional force actually acts towards the right in this case. This only occurs when the engine causes an acceleration of the rear wheels, and we can prove that by noting that if the accelerator is applied aggressively on a dirt road, and let's imagine that this incline is a dirt road, we know that the rear tire would actually produce a force on the dirt and expel the dirt towards the left. And so if the tire is creating a force towards the left, then the road produces a force towards the right. And that is the force that enables the car to accelerate towards the top of the incline. And also, it's important to note that the frictional force will equal the force that's produced internally by the engine. And so, the work done by friction is actually also equal to the work done by the engine. Finally, we need to consider the acceleration, and of course this car will accelerate towards the top of the incline, and this completes our free body diagram. Now in part A of the problem, let's take a look, we're seeking to determine the magnitude of the frictional force. Let's go ahead and tackle that part of the problem. So we want to find the frictional force, and in order to do so, we will apply Newton's second law along the x direction. Now Newton's second law states that if we add the forces along the x-axis, those forces will either equal 0, ma, or minus ma. Of course, the diagram indicates that the acceleration is directed towards the right along the x-axis, so we will choose positive ma for the right side of Newton's second law. We can also note from the diagram that we have two forces that are aligned with the x-axis. We have Wx and we have the frictional force. Note that Wx is entered as a negative force, and the force of friction will be entered as a positive force because it's directed towards the right. And so we'll extend two fingers from this fan and note that we have the frictional force, we have Wx, and on the right hand side we chose ma. Now Wx was calculated earlier, right? Here's Wx, the value is 5880. The mass of the car was 1200, and the acceleration was also given within the problem, here it is, as 5 meters per second squared. If we transfer the 588 to the other side and calculate the right-hand side, the value of friction equals 11,880 newtons. In part B, we would like to determine the work done by the engine. It turns out that the work done by the engine, which we'll just abbreviate as W sub engine, can be determined through the definition of work. That equation tells us that the work done just equals the force times the displacement times the cosine of the angle between the force and displacement. And of course, we're talking about the force that the engine produces. Now we haven't considered the force that the engine produces in our free body diagram because the engine is internal to the car. However, we noted that the force produced by the engine equals the force of friction. And so the work done by the engine simply equals the force of friction, which we just calculated, 11,880. The displacement, which was given within the body of the problem, let's take a look at that. Here it is, the displacement equals 75 meters, as noted in the diagram as well. And the angle between the frictional force and the displacement equals 0 degrees. Let's explore that graphically. Of course, the force of friction is directed along the incline like this. The displacement is also directed towards the top of the incline. And you can see that the angle between these two vectors equals 0. And so the work done by the engine equals 891,000. And hopefully everyone remembers the units for work. The unit for work, of course, is the joule. So this is the amount of work that's done by the engine. In part C, we want to determine the average power delivered by the engine in horsepower. In order to determine average power, we will use the work divided by time equation. That equation looks like this. Of course, we're trying to find the engine's average power. And we found the work done by the engine. However, we need to know how long it took the engine to cause the car to travel 75 meters towards the top of the incline. So time is needed at this point. The work, of course, has been determined in part B. Let's put that in a box. So now we have the question, how do we determine the time required for the engine to propel the automobile towards the top of the incline? Well, it turns out that the car is considered to be an object moving in one dimension, and therefore we will use the 1D motion equations in order to determine the value for time. So let's take a look at those equations. Here they are, and let's take inventory of what is known within this problem. Now the problem notes that the car starts from rest, so V0 equals 0. It also travels a distance of 75 meters, so we know the value for x. And we also know the acceleration, so if we know those three things, we could certainly determine just about anything else. So let's take a look at the 1D motion equations. As I mentioned, V0 equals 0, x equals 75 meters, and the acceleration was given as 5 meters per second squared. We need to solve for time. Let's examine these equations. Can we use the first equation to solve for time? Well, the problem is we don't know the velocity at the top of the incline, so the answer is no. We don't know the average velocity, so equation 2 is not going to work. Equation 3 won't work. Equation 4, let's take a look. X is known, V0 is known. Final velocity is not known, so this equation won't work. Equation number 5 does not contain time. Let's hope that the last equation works for us. We have x known, we have the initial velocity, and we have the acceleration. This is the equation that we're going to use. And so this equation states that x equals v0t plus 1/2 at squared. Now the initial velocity is 0, so this term just goes to 0. And the value for x is 75, so we have 75 just equals 0 plus 1/2 the acceleration times the time squared. 75 would equal 2.5 t squared. We'll divide both sides by 2.5 now and get t squared equals 30, and by taking the square root of 30 we can solve for t. So the time that it takes the car to reach the top of the incline just equals 5.477 seconds. Now the reason we calculated the time, of course, is to enable us to determine the engine's average power, as noted within this equation. So let's bring this equation into our consideration. Again, we left off with average power equals work divided by time. The work that we calculated in part B was equal to 891,000 joules, and we just calculated a time of 5.477, and so the average power for this engine equals 1.627 times 10 to the 5th, and of course the units for power are watts. But the problem requires that we find the power in horsepower, and that's not difficult to do. Horsepower equals 1.627 times 10 to the 5th watts, and we'll convert the watts to horsepower by noting that 746 watts equals 1 horsepower. So we just have to basically divide the wattage by 746, and if we do that, the engine's average horsepower output, which we'll put a bar on top of, equals 218.1 horsepower. In part D, we would like to determine the engine's instantaneous power when the car reaches the top of the incline in horsepower. So we want to find the instantaneous power. That's indicated by P without a bar on top. When the car reaches the top of the incline. Let's take a look at the equation for instantaneous power. Here it is. Instantaneous power equals force times velocity, and we can include a subscript of instantaneous like this. And we should also put this equation in a box for future reference. So let's apply this equation. Now we've already determined the force that the engine exerts, and we connected it to the fact that it equals the frictional force. So this part is resolved. However, we don't know the velocity of the car when it reaches the top of the incline, so we need to find it. And in order to find it, we'll once again rely upon the 1D motion equations. So let's take a look at those equations. Here they are. We would like to determine the velocity at the top of the incline. Let's see if equation 1 will resolve that for us. We're looking for v. The initial velocity is 0. The acceleration was given, and we also determined the time required for the car to reach the top of the incline. This is the equation that we'll be using. And so from 1D motion, the velocity just equals v0 plus at. The initial velocity is 0, the acceleration is 5. We calculated the time to equal 5.477, and if we multiply those two numbers together, we obtain a velocity of 27.39 meters per second. So that's the velocity of the car at the top of the incline. And now we'll just substitute that value into the power equation. And that will yield, again, force times velocity. The frictional force was equal to, here it is, 11,880 newtons. We'll multiply that by the velocity, which is 27.39. And if we multiply those two together, we obtain 3.253 times 10 to the 5th watts. We would like to express this in horsepower. We'll just apply the same procedure that we used earlier. And so to determine horsepower, we'll just take the 3.253 times 10 to the 5th watts, and we'll note also that 746 watts equals 1 horsepower. Of course, the watts cancel and horsepower remains. And so the instantaneous horsepower equals 436.1 horsepower. And so let's compare this with the average horsepower. On average, the engine was only producing 218.1 horsepower. But as the velocity increases, as noted within this equation, the engine has to produce more and more horsepower in order to continue to propel the car under these circumstances. And so we're noticing that in order for an object to travel at a high velocity, the engine that's driving it must have a substantial amount of horsepower. In Part E, we would like to determine the work done by gravity. In order to determine the work done by gravity, we'll just apply the definition of work. And of course, work is just defined as, in this case, the force of gravity times the displacement times the cosine of the angle between the force of gravity and the displacement. Now, as we noted earlier, the force of gravity, of course, just equals the weight of the object. And it's important also to identify the angle between the weight and the displacement. Now, we know that the weight is directed downwards. We also know that the displacement is directed along the incline, like this. We need to determine this angle in here, in between those two vectors. And how do we do that? Well, in order to determine that angle, what I'll do is extend the delta x along the incline. Then we'll connect it and actually trace out the incline like this. And we'll just do some basic trigonometry or geometry to determine this angle. We know that this angle was given as 30 degrees. We also know that the sum of the angles in a right triangle must equal 180. The other way to look at it is the two acute sides, or the two acute angles within a triangle, must equal 90. And so if this angle is 30, this angle is 60. We should also note that the large angle along the incline equals 180 degrees. And so the 60 plus this theta have to equal 180. And so what is the value for theta? Well, if this is 60, we need another 120 degrees in order to obtain 180 degrees. And so theta just equals 120 degrees. And so the work done by gravity just equals the weight, which is of course the force of gravity, times the displacement, times the cosine of the angle. Now we calculated the weight as 11,760. The displacement was 75 meters, and the angle we just determined equals 120 degrees, and therefore the work done by gravity equals negative 441,000. And the units, of course, for work are joules. Now, the reason we obtained a negative, of course, is because gravity opposes the motion of the car. So this negative means that gravity, which of course creates the weight of the car, opposes the car's displacement. And that completes this lecture.